numbers which can be placed into the form of a fraction are called rational numbers. And a formal definition looks like this. Rational numbers are numbers that can be put into the form a over b, where a and b are integers and b is not equal to 0. Now, think about why b cannot be equal to 0. Remember, we said that if a denominator is 0, then the fraction is undefined. So to avoid that situation, we restrict b to values other than 0. Some examples of rational numbers are these. 1/2 clearly is in this form. -3/4 clearly in this form. Now, realize that -3/4 can be written like this, as -3/4, so this too then is a rational number. Any number which can be put into that form is a rational number. 1 3/4, well, it doesn't look like it's in that form now, but it can be put into that form rather easily. A mixed number can be written as an improper fraction. 4 times 1, 4, and 3, 7/4 then would be the pure rational form for this mixed number. Now, whole numbers like 5 can be put into that form as well. Just write the whole number over 1, you see, and it's in that form. And if it can be put into that form, it's a rational number. Same idea with -7. All integers then can be put into that form because we can write this as -7/1. Well, we don't have listed here any decimals, but clearly some of the fractions that we see here can be put into that form as well. Or, excuse me, some of the fractions that we see here have decimal equivalents, so decimals then are rational numbers as well. For example, 3/4 is 75/100, a decimal, but it has a rational form. You see, it can be put into the form of a rational number, so this then is a rational number. And sometimes fractions lead to repeating decimals. And here, 2/3 is 0.666666 forever. And the little mark on top of a digit means that that digit repeats. Now, I could have listed it a little more simply. I could have said, well, this is 0.6 and put that little bar over the 6, and it just means the 6 continues on forever. All right, so terminating decimals. This is a terminating decimal because it kind of stops. If we were dividing 4 into 3, we would stop the division right here. But 2/3 is a repeating decimal. There is a digit which repeats, and repeating decimals may have more than one digit which repeat. And I'll show you an example in a second. The idea is that decimals which terminate or repeat are also rational numbers because they can be put into the form of a rational number. Now, 45/100 and 2.706, these are terminating decimals. They're rational numbers. Now, here is an example of another rational number, and notice that we have to the right of the decimal point 252525 and the little bar over the 25. And that just means that 25 repeats. Now, a simpler way to write this one would be as just like this. I didn't have to write all of those 25s, but these mean the same thing. Here we have 3 digits that are repeating, and this just means that this is 0.123123123 forever. All right, so that's the idea. Now, we're not so much interested in this section with trying to identify rational numbers. We've identified enough of them, and we have a good feeling about that, I think. But we want to perform operations on rational numbers, and that means performing operations on fractions and decimals, but now the fractions and decimals may carry a sign. They may be positive or negative, and that's really what we want to concentrate on here. All right, remember that when we collect fractions, when we add or subtract fractions, we need common denominators, and common denominators are also least common multiples, and we had a strategy for finding least common multiples. Now, sometimes, as is the case here, we can see through the problem and we can tell that the common denominator here would be 4. And we imagine, well, gee, if 4 is the common denominator, then we change both fractions into the common denominator. And if we were going through that process, we would do this. For the first fraction, we would write the 4 in the denominator, and we would say 2 goes into 4 2 times. 2 times 1 is 2 to get this minus 2/4, you see. And writing the 2 fractions as with common denominators allows us to bring together the numerators. So at this point, once we have common denominators, we say that we bring together numerators. It's -2 plus 1 for our new numerator, and it's over the common denominator. Now it's just a matter of collecting the integers that appear in the numerator. So let's see, negative 2 plus 1, that turns out to be negative 1. So this is negative 1 over 4, which can be written as simply negative 1/4. Now remember, this minus sign in the numerator can float. There are really three signs in a fraction. There's the sign of the numerator, the sign of the denominator, and the sign of the fraction itself. And it's often the case that when a single minus sign is in a fraction like this, that we actually move that minus sign as the sign to a position where it's the sign of the fraction. Here's another one. We have negative 3/5 minus 2/3. Now there are a few ways of looking at this, but we're just bringing together these two fractions, and we can think of this as negative 3/5 plus negative 2/3. You see, that's a kind of a good way to look at it, but we don't have to write it that way. We can just say, gee, we're bringing together two negatives, you see. Now, we go through the process using the strategy that we know about with fractions, and that means finding a common denominator. Now, our common denominator, remember, is the least common multiple for the denominators, and that least common multiple can be identified by looking at a factored form, by looking at factors. Now, we have a prime factor here in this denominator and a prime factor in this denominator. And remember, the least common multiple contains every different prime factor that we see. And sometimes we'll see that prime factors appear more than one time. That is, there's an exponent on them, and we'll have a look at that in just a minute. But if the least common multiple contains every different factor that we see, then we see a 5, we see a 3. You see, and so the least common multiple is 5 times 3, or 15. And now the trick is to change both of these denominators into a new one, which is 15. And to do that, and a lot of times we do a lot of this in our heads, but it's important to realize the complete idea of what we're accomplishing, and that is to make these two denominators 15. Now, one way to do it is to just write 15s down, like write this 15 and say 5 into 15 goes 3, 3 times 3 is 9 to get this 9. Another way, and a more mathematically sound idea for this, reason why all of that works, is that if you think of transforming this negative 3/5 into a new fraction with a denominator of 15, then you would have to multiply in the denominator by 3. But if we multiply in the denominator by 3, we have to also multiply in the numerator by 3, because what we're really doing is multiplying by 1. And multiplying by 1 doesn't change the value of the fraction, but it changes its form. It'll look different, but it has the same value. All right, that's the whole idea here. Now, multiplying straight across, we get the negative 9/5. And here, for this one, we're changing into 15ths, so we need to multiply the denominator by 5, and therefore the numerator also by 5, to multiply by a form of 1. And going straight across, we find this to be 10/15. All right, once we have the common denominator identified and the fractions changed into the common denominator, we collect numerators. This is negative 9 minus 10, you see, minus 9 minus 10 if you'd like to read it that way, all over the common denominator 15. Now, we talked in a previous section about collecting integers like this. You see, same sign, add the digits and attach the sign, attach that common sign. So add 9 and 10, we get 19, and attach the minus sign. So negative 19 over 15. Now, there are a number of ways of representing this. We can let the minus sign float to the sign of the fraction, but it's an improper fraction, and we would probably write this as a mixed number. So we could write it like this, minus sign as the sign preceding 19 over 15, but 19 over 15 becomes, let's see, 19 divided by 15 is 1 with 4 left over, so it's 1 and 4/15, negative 1 and 4/15 as a mixed number. Let's do another one. Let's make the denominators a little more difficult to see through. 5/16 minus 7/40. Now, we mentioned several strategies for finding that common denominator, or the least common multiple. And one rather formal kind of strategy is to go through a prime factorization for both of the denominators. But it's a sure way of identifying the correct least common multiple. And let me show you how that works. We want to identify least common multiple. Okay, so we go out to the side and we say, gee, it's not evident here. So what I want to do is take 16 and go through a prime factorization. So over here, for the least common multiple, this is the process of finding it, taking 16 and I'm kind of just dividing it up, or I want the smallest items, the smallest factors that I can identify that are multiplied together to give 16. So I think of 16, since it's even, I can think of it as 2 times another factor. The other factor is 8. So 16 is 2 times 8, and then I look at the 8. Oh, 8 can be written as 2 times 4. You see, so I bring down the first factor and write 8 as 2 times 4. I bring down these factors and write 4 as 2 times 2. Now I have a string of prime factors, and I can use an exponent to sort of write them all together. This is 4 factors of 2. Oh, that's 2 to the 4th power. And in a similar way, I can go through the prime factorization for 40. 40 is even, so we can write it as 2 times another factor. The other factor is 20, so 2 times 20 is 40. Bring down the 2. 20 is 2 times 10. Bring down the 2's. 10 is 2 times 5. Now I have a string of prime numbers, you see, as factors. And I have 3 factors of 2, so that's 2 cubed times 5. And now I can look at these two and identify a least common multiple. The least common multiple will contain every different factor that we see. We see 2's here, and a 5 here. The only different factors that we have are 2's and 5's. Now, so we're going to have 2's and 5's in our least common multiple, but how many of each of these are we going to have? We have 3 2's in 40, we have 4 2's in 16. And it turns out that for the least common multiple, we want to identify the most number of times that any factor, any common factor may appear. So 2 appears 4 the most number of times. So our least common multiple is 2 to the 4th times 5. Now when we multiply this out, it turns out to be 80. Now we can write it simply as 80, or we can leave it in this sort of factored form. So our least common multiple is 2 to the 4th times 5. Leaving it in the factored form kind of helps us a little bit to identify what factors are needed in our denominators. What are we going to multiply into these denominators, you see, to change into this? And we can tell like this. It's 2, excuse me. You see, this is our common denominator, and here's our common denominator again in the other fraction. Now, we might say 16 goes into 2 to the 4th times 5, or 16 goes into 80 how many times? That's a way of trying to deal with it, but we have the prime factorization of 16. It's written right over here. Let's have a look at it. 16 was 2 to the 4th. You see, so we have 2 to the 4th already in the 16, but we want 2 to the 4th times 5. Oh, we're missing the 5 factor. So we need to multiply this fraction by 5 over 5. That's the idea. So when we multiply in the denominator by 5, we get this. When we multiply in the numerator by 5, we get 25. And now for the other one, same idea. We're changing 40 into 2 to the 4th times 5. Gee, what are we missing in terms of a factor? Well, we need to go and look at the prime factorization of 40 to see what's missing. And we look down there and we see that it was 2 cubed times 5. Oh, and here we want 2 to the 4th times 5, so we're missing a factor of 2 in that 40. So we multiply this by 2 over 2. Multiplying the numerator by 2, we get 14, and in the denominator we get 2 to the 4th times 5. But as I say, there are a lot of right strategies to use here, and you're going to find one that's comfortable for yourself. So it's the idea that this really is, and I'm just going to write a step to just show it in a different form. This is really just 25 over 80 minus 14 over 80. And now we're collecting numerators. We think of this as 25 minus 14 all over the common denominator 80. And when we subtract, let's see, we get 11 over 80 as the result. This next problem involves rather simple fractions, but there are 3 of them. we want to bring all of them together. And to do that, the strategy is exactly the same as it has been. That is, we want to identify a least common multiple or a common denominator, change all the fractions into that common denominator, and then collect numerators, you see, and write that collection over a common denominator. All right, let's go through the problem like this. I'm going to remind you of another strategy for finding least common multiple, and this works pretty well when the numbers are fairly small. Now, and these numbers are fairly small. What you do is you take the largest of the denominators and you think about multiples. And every time you think about a multiple of 8, in this case, you ask yourself, do 4 and 6 go into that multiple? You see, and if you string out multiples far enough, you're going to find a hit. That is, you're going to find a multiple of 8 that these two other denominators go into. And you would go like this. All right, you write the 8. Does 4 go into 8? Yes. Does 6 go into 8? No, not evenly. All right, the 8 times 2 is 16. Does 4 go into 16? Yes. But does 6 go into 16 evenly? No. So let's see, 8 times 3 is 24. Does 4 go into 24? Yes. Does 6 go into 24? Yes. And of course 8 goes into 24 because it's a multiple of 8. So we have struck a common denominator or a least common multiple for all three of these denominators. And so we would go through the process of changing the fractions. Just write the denominators in here. Let me go through that little process. Here's how we're thinking about it. We would write this in our next step. Once we have the common denominator, just write these signs that precede the fractions. Write the common denominators in, and then go through that little process of saying 4 into 24 goes 6. 6 times 3, 18. You see, and then 6 into 24 goes 4. 4 times 1, 4. And then 8 into 24 goes 3. 3 times 5, 15. Now that we have common denominators, we collect numerators. So we have negative 18 plus 4 minus 15 all over the common denominator 24. And now it's just a matter of collecting these integers in the numerator. Negative 18 plus 4 is negative 14. Bring down the negative 15. Collecting these two, the signs are the same. So we add the digits and attach the common sign. 14 and 15, 29. Common sign is negative. Negative 29 over 24. Oh, I see, it's an improper fraction. I would probably want to write this minus sign preceding the mixed number. So I would write this as the negative of, or the opposite of, or minus. Let's see, 29 over 24. 24 goes into 29 one time with 5 left over. So this is 1 and 5 24ths. And our answer then is negative 1 and 5 fourths. Suppose we want to bring together these two decimals. It is 47 and 34 thousandths plus a negative 56 and 91 hundredths. You see, we're trying to bring these two together. Now, if you get confused about what to do in a situation like this, you can always change the problem into a much simpler one that you can see through rather easily. Now, all we have here is a positive number plus some negative number. So if you get confused about, oh, do I change the sign, or do I want the sign of the big one or the sign of the, that kind of thing. If you get confused, just think about, well, let's see, this is this 56 in terms of just digits now is a larger number than the 47. So if we had something like 4 plus a negative 8, let's say, what would we do? And figure out what you would do in this circumstance and apply it to the more complicated looking problem. A lot of times you can get yourself out of big trouble in math using that kind of strategy. Okay, the idea here is that we can think of this as adding a positive number with a negative number, or we can transform this into, you see, we can kind of drop that parenthesis and think of this like this. You see, because we know that subtracting a number is the same thing as adding the opposite of the number. So these just are interchangeable ideas. And some people like to see it like this, other people like to see it like that. But they mean the same thing. Now, we're bringing together numbers that have unlike signs. And remember that in that process, one strategy is to look at the digits involved and just take the number with the larger digits, you see, and subtract the number with the smaller digits. Take the big number and subtract the small number. That's the idea. So we really want to take this 56.91 and take away the 47.034. Now we know we're going to attach the sign associated with the larger one. You see, our answer is going to be negative. And I'll even write that down. It's going to be a negative result. But in order to find the digits here, we have to take the relative difference between these two. So that process, we go to the side, we go underneath, wherever. Let's see. Here's what we're doing. We're taking the 56.91 and we're subtracting the 47.034. And we're doing this just to identify the digits that will be in our answer. You see, and now we need a 0 as a placeholder, and away we go. We can't take 4 from 0. We borrow from the 1. When we borrow from the 1, it becomes 0. This becomes 10. 10 minus 4 is 6. 0 minus 3, can't do that. Borrow from the 9, it becomes an 8. The one that we borrow makes this 10. 10 minus 3, 7. 8 minus 0, 8. Decimal comes straight down. 6 minus 7, oh, it won't go. So we borrow from the 5, it becomes a 4. The one that we borrow makes this 16. 16 minus 7 is 9. So we have 9.876, and these are the digits then that follow this minus sign. So negative 9.876 is our answer. Now, the process, when you first look at problems like this, you have decimals involved, we have positive numbers, we have negative numbers, and we have to decide how to put them all together. Just take your time. Just go slowly with the thought process here. And as I say, one good strategy is to degenerate the problem into a simpler problem with the same characteristics and decide what you would do and then apply that idea back in your problem here. All right, let's look at another one. This one is very similar to the one before, and I want to show it again because this is the most difficult situation, I think, involving the collection of decimal numbers. You see, if the signs are the same, it's pretty easy, isn't it? Because if both signs are plus or both signs are minus, we just add the digits and attach the common sign. So that's pretty simple. It's when the signs are different that we run into some kind of difficulty, as is the case here. So we have understood plus 16.127 minus this number. You see, signs are different, so we want to subtract digits and apply the sign of the larger of these two. You see, we're subtracting digits without regard to sign, and then we look at the sign of the larger one, that's minus, again, in this case. So our answer is going to be minus or negative. But to identify the digits involved, we take the relative difference in the digits. So we take the number with the highest digits, if you will, the 67.91, and we're going to subtract the 16.127. And away we go. Just like we did before, we need a 0 placeholder here. 7 from 0 won't go. We borrow from the 1, it becomes 0. The one that we borrow makes this 10. 10 minus 7 is 3. 0 minus 2 won't go. This becomes 8. The one we borrow makes this 10. 10 minus 2 is 8. 8 minus 1, 7. Decimal point straight down. 7 minus 6, 1. 6 minus 1, 5. So 51.783. follows that minus sign. Here's a situation where we have 3 decimals that are to be collected or brought together. And in a circumstance like this where maybe you'll have a string of 6 or 8 of them, and you want to look at the ones that have the same sign, I think, is a good strategy. You could just go left to right and pick them off sort of 2 at a time. Just do them in pairs from left to right, and that's fine. But another way to attack the problem, and sometimes it's a simpler way, is to take all of the ones preceded by a plus sign, bring those together. All the ones preceded by a minus sign, bring those together. Because we know that when the signs are the same, we add the digits, and that's a little easier than subtracting. So here I might look at these two and say, well, gee, I'd like to bring those two together first. And by the way, this plus negative 3.6 could be rewritten as simply minus 3.6. Means the same thing as this does. All right. But at any rate, we notice that the signs are the same on these two, and therefore we can add those two. Let's do that down here. This is 1.02, and I'm going to add the 9.26. 6 and 2, 8. 0 and 2, 2. Decimal straight down, 1 and 9, 10. So those two together is 10.28. I'll put that information up here. 10.28. And now I can rewrite this if I want. I can leave it like this, plus negative 3.6 if I want to, or I can write it as minus 3.6. In either case, I see that the signs are different, and so I'm going to subtract digits. I take these digits, and I subtract those digits. 8 minus 0, 8. 2 minus 6 won't go. Borrow from the 10, can't do. Borrow from the 1, it becomes a 0. The one that I borrow makes that 10. I borrow from the 10, it becomes a 9. The one that I borrow from the 10 makes this 12. 12 minus 6 is 6. Decimal comes straight down. Then 9 minus 3 is 6. So 6.68 then is our answer. And 6.68. And remember, the sign preceding these digits would be the sign associated with the larger of these two. Oh, it's this one, understood to be plus, understood to be plus. This is our answer. When it comes to multiplying and dividing, the rules are exactly the same as the rules that we learned before. And that's true, that's been true all along. That the rules for adding, subtracting, multiplying, and dividing, fractions and decimals, are in play here. The only thing that's really different in these problems is the trick of dealing with positive and negative numbers, and that's what we're trying to emphasize here. But notice that the rules are the same rules that we learned before. So when we're multiplying a couple of fractions like this, the idea is to multiply straight across. And remember, we have the cancellation possibility when we're multiplying fractions. And we notice here that we have a negative number times a positive number. The signs are different, so we get a negative result. So we know our answer is going to be negative. And I encourage you to try to separate the problem into little problems. And one little problem here is to identify the sign of the answer. You see, and that's kind of like one event in the overall solution to the problem. So let's take care of that event. Identify the sign of the answer. It's minus. Done deal. All right, now let's go on about the business of multiplying the digits. We're looking for cancellations. I see a possible cancellation here between the 8 and the